determine that runtime for a particular algorithm. That is why we have the notations that we use under asymptotic algorithms. And the three basic notations that we commonly know, this is the big O, the omega, and the theta notations. And those three notations are the same notations which also give us a way of coming up with a conclusion to say this is the average case, or when we talk of the runtime, this is the best case and the worst case. These are reflected by the three notations that I have stated. So now I am now taking you to this segment on properties. The common properties of the asymptotic algorithms. In this case, I will dwell on 5 properties. The first property, this is the general property. The general property, it states that if a function is given as OG of n, then a, remember a is a constant, and in this case, a is multiplying a function. Then a multiplied to a function is also OG of n. So if you look closely to these two functions, there is no difference, there is no adjustment. Then property number 2, it states that if f of n is OG of n, then this g of n is OH of n. Then the function as a whole, it becomes OH of n. That is what the transitive property states. Then the third property, which is the reflexive property. This one states that if a function is given, then f of n is OF of n. This one is the most straightforward property of all the properties. Then the fourth property, we have the symmetric property. This one states that if f of n is theta g of n, then g of n is theta f of n. So what happens is, whenever you are given a problem to solve, you are now solving this mathematically using figures. Given the figures, you can now substitute for the letters that are given. Then the fifth property, which is the transpose symmetric property, it states that if f of n is OG of n, then g of n is omega f of n, and this property satisfies both the big O and the theta notations. So having looked at the general layout of the properties of algorithms, I would want to look at the graphical representation of the asymptotic notation, which is the big O, the omega, and the theta notations. How do we represent these? The big O notation. The big O notation, we can graphically represent it as something of this nature. Remember, the big O notation, this one, it reflects the upper bound of a given algorithm. So this g of n now is standing in for the bound of that particular graph which you are given. So in this case, this is the big O. The big O represents the notation, this one reflects the lower bound of a given algorithm. So this becomes your g of n, and this will always be your function. And where these two graphs meet, we have a k there, which is taken as a constant. So the omega notation can be simplified graphically as I indicated there, and it represents the lower bound of an algorithm. So this will also represent the minimum time required for an algorithm to execute. Then the third notation becomes the theta notation. The theta notation is denoted by this symbol. Then graphically it can be represented as follows. This becomes the function. Then this is the upper bound, which is the g of n. Then this will be the lower bound. You can shade this region. So what it simply means is that the theta notation, it accounts for both the upper bound and the lower bound, which means it takes note of both the big O and the omega notation. So basically these are the graph or the graphical representations of the three notations that we commonly use. Then we can, as we move on to the differences between these notations, the general difference